All right, James had a question about the NASA program. I put part of an email I received from whoever the lady is, I think at Oklahoma State or somewhere, that sort of coordinates the program. I posted that in the Cal 3 course and in the differential equations course because there was one guy in differential equation who's not in Cal 3, but the three of you are in both of those classes, so I thought, why post it under linear algebra, because we all will see it in two other places. So I didn't post it in this class, not to slight this class any, but just I didn't see any need because I knew you would see it otherwise. It's a great program. We've had several students participate in it in the past, and from all I know, they've all enjoyed it immensely. They've learned a lot. They've made a lot of contacts, networking. There's just a lot of benefits to that, and it's fun. From what I understand, it's a lot of fun. Could be some work too, but I think it's pretty rewarding type work. So if you're interested, check it out. It's I know NASA wants community college students involved, and it's just a great opportunity. All right, any other questions, issues, concerns before we get going on linear algebra today? Now, where we're going to start today, before we start there, if you've got a book open in front of you, flip back to page 55. And on page 55, example 5 on that page was basically this. They showed you three matrices, A, B, and C. And what they had you do is show that AC was equal to BC. This was back when we were just learning to multiply matrices. And you saw those were indeed true. But what we also saw was that A and B were not equal to each other. Okay? Even though AC was equal to BC, A and B were not equal to each other. And we said at the time, the title of this, an example in which cancellation is not valid. Just because it's the same matrix C, you multiply by both of them, you can't say, well, let's just divide out the C. Well, number one, you can't divide matrices. That was not true. However, where we're starting off today, this is about 14 pages late. Oh, here's Jesus, I'm sorry, I said it wrong. Hang on just a minute. Let me get it marked in the book. Perfect attendance today, folks. Way to go. Love to see it. Okay. And, Jesus, can you hear me yet? Okay. Hopefully you can. All right, good deal. Earlier there was just a comment or question about the NASA Community College Aerospace Scholars Program. Just general information because I had posted some stuff on it. What my comment was, we've had students for several years participate in that, Lawson students, and by and large, everyone I've heard from thoroughly enjoyed it. They found it really interesting, a learning experience. There may be some work involved. I imagine there will be, but it's been with good people, good contacts, good networking, and just a fun time with learning as a big key to it. So I posted that on both the Cal 3 class and the differential equations class because there was one guy in differential equation who wasn't in Cal 3, but then all three of you were in both of those classes, so I figured y'all would get to see it, but I posted it in both of the others, so everyone would get to see it. So don't feel like I was slighting this class any. It's just you got to see it in two other places. Same announcement you'll see in both places. That's the same one I would have posted here, but I thought, why? What's the point? Okay, so anyway, we just talked about back on page, what page did I say it was, 55? We saw an example example 5 in section 2.2 that showed that you can't necessarily cancel out just because AC was equal to BC. That doesn't mean A is equal to B. Okay? Yet, where we're going to start today, unless there's a question otherwise, on page 69, middle of the page, this is chapter 2, matrices, 2.3, inverse of a matrix. We start with theorem 210, and guess what theorem 210 says? If, now I got the wrong end of my pen. Here's what theorem 210 says. If C is invertible, that means C does have an inverse, an invertible matrix, then the following properties are true. If AC equals BC, exactly like we saw over here, then now it does imply that A is equal to B. So what is that? Is that a contradiction? No, what that's telling us, that C matrix we had in that problem back on page 55 must not have been an invertible matrix. So let's just go back there and see. That C matrix was, that we had before, in that problem, C was equal to 1, negative 2, negative 1, 2. Now that's a negative 1. I don't know why it chose to write that way. I did not do that. The pad did that. Negative 1, 2. Okay. Guess what? That's not an invertible matrix. How do we know? Row 2 is a multiple of row 1. Row 1 is a multiple of row 2. Column 2 is a multiple of column 1. Column 1 is a multiple of column 2. It is not an invertible matrix. Okay? How do we check that? Check the determinant. So 2 by 2, this would be 2 minus 2 equal 0. If the determinant is 0, it's not invertible. So that's why it was not true here, but it is true here. If C is an invertible matrix, then you can, and this is called a right cancellation, but it can also be that if CA is equal to CB, that was my uncle's initials, that implies that A is equal to B. Okay? So that's called left cancellation. So you can do this if C is invertible. If C is not invertible, no, you can't make that assumption. Okay. Now, let's take, we're going to do the little proof because it's pretty easy. Let's take this one. Well, in fact, let's do this one since it's right here. What we could do here is multiply both sides of this equation by C inverse, because it is an invertible matrix. So C inverse times CA has to be equal, because this is equal to C inverse times CB. Well, guess what? C inverse times C, since it's an invertible matrix, that's the identity matrix. Okay? And C inverse times C here is the identity matrix of the proper size times B, and I times A is A, and I times B is B. So we then proved that was true. Pretty easy proof. And some of these proofs in linear algebra are just about that simple. Others of them can get pretty convoluted. So I don't usually waste a lot of time or spend a lot of time on the proofs, as you noticed. All right, the last section here then, any questions on that? So just because we said it wasn't cancelable here, that's only because that C was not invertible. If C is invertible, see, back in that section, we didn't even talk about inverses yet. We didn't know what they were yet. But if C is invertible, then you can do this. All right, any questions? So let's see, what I want to do is clear my drawings. Okay? Now, some of you don't have access to a book at the same time you're watching this. I think I've asked that several times before. Here, I don't know. I guess I'll write it out. I wanted to sort of type it. Now, what we're going to say here applies to square systems. Now, what do we mean by square systems of equation? Those that have the number of rows, okay, the number of equations equals the number of variables. That's what we mean by square systems of equations. Number of equations is the same as the number of variables. If that's the case, this theorem holds. It's theorem 211. Systems of equations with a unique solution. If A is an invertible matrix, okay? Now, number one, that means it's a square matrix. This is a square system, that's a square matrix. If A is an invertible matrix, then that implies the system of linear equations these are all abbreviations here, linear equations, AX equal B. By the way, this X is a vector, and that B is a vector, okay? Has a unique solution X, vector X, that's your unknown vector, is equal to A inverse, I'm sorry, I shouldn't write that. A inverse times B. Okay? Now, again, this has a little proof. We start with this, and we know A is invertible. And if A is invertible, that means it has an inverse. A inverse. Multiply on the left, this, and multiply this on the left. Okay? Well, A inverse times A is the identity matrix again. And that times the variable vector is equal to this. And since I times a variable vector is going to be that variable vector, this is the same as that. Pretty straightforward. Okay? Now, is this the way then to solve a system of equations? Generally not, okay? You can, of course. But you see, on this system, you first have to get the row reduction of A and augmented with the identity matrix to get your inverse matrix. And then once you got your inverse matrix, multiply that by your B vector. So that's Gauss-Jordan elimination, or Gaussian elimination, or Gauss-Jordan. Let's use Gauss-Jordan. All you have to do is put the coefficient matrix, augment that with just the B vector, do your elimination, and you got your answer. That's much quicker than finding the inverse and then doing the inverse times that constant matrix. Unless you have, as it says here, solving several systems that all have the same coefficient matrix. See, if you have AX equal B, just one of those B's here, then just go and do Gauss-Jordan elimination for sure. But if you're trying different B's for the same coefficient matrix A, every time you do a new B, you have to go back and do the whole Gauss-Jordan elimination again, because you've got this new row here, or column here. But if you do this, just do that once to get your inverse matrix, and then all you have to do is multiply that by all the different B's you have. This is an easier process than doing Gauss-Jordan over and over. So if you got more than one possible B's for the same A, use this technique. If you've only got one B you're interested in, do Gauss-Jordan elimination. Okay? So I'm going to erase what we got on the slide here. Any questions before I erase it? Okay, I'm going to show you what our problem is here. Here's our problem. It's a long problem to write. 2x plus 3y plus z is equal to minus 1. 3x plus 3y plus z is equal to 1. 2x plus 4y plus z is equal to negative 2. Okay, there's the first system of equation we want to solve. The next one, the coefficients, the left-hand side of, on the left of all three of those equal signs, exactly the same, but this time they're equal to 4, 8, and 5. The C one, exactly the same system of equations on the left of the equal sign, is equal to 0, 0, 0. Okay? Now I can tell you the answer for the last one right now, but I'll wait and not do it. Okay. Now if you did Gauss-Jordan elimination, you would have to do it for the first one, then you'd have to do it for the second one, then you'd have to do it for the third one, though I can tell you the third one already. Okay? But doing the way we just said, finding first the inverse matrix, it makes it a piece of cake. Now the inverse matrix is harder to do than Gauss-Jordan elimination on any one of them, but it's easier to do than doing 3 Gauss-Jordan eliminations. Okay, so here's what we do. 2, 3, 1, 1, 0, 0. This is to get our inverse matrix. 3, 3, 1, 0, 1, 0. 2, 4, 1, 0, 0, 1. Okay. Now what we want to happen first is to have a 1 in the upper left. A big boo hiss, we don't have it. We could get it by dividing everything here by 2. This would make this 1.5, that would make that 0.5, that would make that 0.5, that would keep that a 0 and a 0. Well, that has 3 fractions or decimals in them, okay? If you did the same thing here, you would have a 1, divide everything here by 3, you have a 1, 1/3, 0, 1/3, and 0. Well, number 1, you only have 2 fractions, but they're not, you have to write them as fractions, not repeating decimals, because the decimals keep repeating. Down here, if you did the same thing, you would have, where is my pen now? There it is, okay. Divide by 2, you'd have 1, 2, 1/2, 0, 0, 1/2. I like that better. So the first thing I'm going to do is swap row 1 and row 3, and at the same time divide row 3, which is our new row 1, by 2. Okay, so my new row 1 will be 1, 2. Now, do you like decimals or do you like fractions better? Anyone have a preference? Let's stay with fractions then. 1/2, 0, 0, 1/2. Second row we'll leave alone. 3, 3, 1, 0, 1, 0. Third row is going to be what was my first row. 2, 3, 1, 1, 0, 0. Okay. I'm about to lose my voice again. Hold on. This is just way too much talking. Teaching 4 classes on Tuesday and Thursday and 3 on Monday and Wednesday. I'm wearing out my throat here. And I talk too loud. Sorry about that. All right, what's next? Okay, we finally got our 1. If I can find my pen here where we wanted it. We need a 0 here and here. Well, let's deal with this one first. -3 times row 1 plus row 2 will give us our new row 2. So since we're using the top row, row 1, write it down. 1, 2, 1/2, 0, 0, 1/2. Okay. Now do the operation called for. 3 times 1, or -3 times 1 is -3 plus 3 is 0. Good. -3 times 2 is -6 plus 3 is -3. Okay. -3 times 1/2 is -3/2 plus 2/2 is -1/2. And 0 plus 0 is 0. And 0 plus 1 is 1. And -3/2 plus 0 is -3/2. Okay, now what we want next is that 2 to become a 0. So how do we make that happen? -2 times row 1 plus row 3 is the new row 3. Okay, so let's do it. -2 times 1 is -2 plus 2 is 0. Yep, we got that. -2 times 2 is -4 plus 1 is -1. -2 times 1/2 is -1 plus 1. Ha, that's a 0. -2 times 0 plus 1 is 1. -2 times 0 plus 0 is 0. And -2 times 1/2 is -1 plus 0 is -1. Okay. All right, what do we want to happen next? Well, let's review what we got and where we want to be. If I can see, there's my pen. We got a 1 here, 0 is below it. I want a 1 right here, but that's a -3. Now I could divide by -3, and that becomes a positive 1/6, 0, negative 1/3, and positive 1/2. Ew, that's a lot of fractions. Why don't we exchange these two rows, at the same time negate this row here? Okay, I know this is cheating, it seems like, but it's not. I'm just combining a couple steps together. So if I can find my pen, there it is. Okay, I'm going to do what I just described down here. Top row stays the same. 1, 2, 1/2, 0, 0, 1/2. Excuse me just a moment. My throat's wearing out, but now I feel like my eyes are wearing out. It's getting harder and harder to see and to focus. I don't know what's going on. Maybe my glasses are dirty. I don't know. Seems like they're okay. Okay. So what I'm going to do is swap these two rows and negate this, the third one, make it the new second one. So that's going to be a 0, 1, 0, -1, 0, 1. Okay. And the new third row is going to be a 0, -3, -1/2. That's an ugly 1/2. I don't know why the pad does that. 0, 1, and -3/2. Okay, let me see if I can make that 1 look a little better. Okay, I think that's a -1/2. -1/2. Okay, not much better, but a little bit. Okay, now what do we want to happen next? We want that 2 to become a 0. So what we'll do is -2 times row 2 plus row 1. -2 row 2 plus row 1. Sorry I have to talk so slowly, but I found that if I slow down the pen, it makes fewer mistakes. Okay, so we're using the middle row. Write that down. 0, 1, 0, -1, 0, and 1. Okay, now -2 times 0 is 0 plus 1 is 1. Yeah, we didn't want that to change. -2 times 1 is -2 plus 2. That would be a 0. That's exactly what we wanted. -2 times 0 is 0 plus 1/2. Unfortunately, that's still 1/2. Okay, -2 times -1 is +2 plus 0. That would just be 2. And -2 times 0 is 0 plus 0 is 0. And -2 times 1 is -2, or make that -4/2 plus 1/2 is -3/2. Okay. Now, the third row, we want that to become 0, so we're going to do 3 times row 2 plus row 3. Alright. I think part of my problem here is just absolute hunger. Okay, so sorry a minute. That's not much to calm the stomach, but it'll maybe do a little bit. So let's do that. 3 times row 2 plus row 3. 3 times 0 is 0 plus 0 is 0. That's good. We didn't want that to change. That was an extraneous mark. 3 times 1 is 3. Minus 3 is 0. Let me go on and get that extraneous mark out of there. Okay. Sorry, my throat hurts so badly. 3 times 0 is 0. Minus 1/2 is minus 1/2. 3 times minus 1 is negative 3. Plus 0 is minus 3. 3 times 0 is 0 plus 1 is 1. And 3 times 1 is 3. I'll make that 6 halves. Minus 3 halves would be 3 halves. Okay, I'm doing this fast. I hope I'm not making any mistakes. Boy, I feel like I'm about to drop. Okay. Now, generally, the next thing we want to happen is this minus 1/2 to become a 1. But not yet, because what we want to do is to make that become a 0. So leaving it as, we can just add row 3 to row 1. That'll make that be a 0. Then we can come back and make this. So let's do that. What we're going to do is add row 3 plus row 1. Sorry, I have to write so slowly. 0 plus 1, wait, let me get my matrix in here, is a 1. 0 plus 0 is 0. Negative 1/2 plus 1/2 is 0. That's why we did it. Negative 3 plus 2 is a minus 1. 1 plus 0 is 1. And 3 halves minus 3 halves is 0. Oh, that worked out nicely, didn't it? Okay. Second row I think is perfectly good the way it is. 0, 1, 0. Negative 1, 0, 1. Now the third row, what we're going to do is minus 2 times row 3. That will make that become a 1. That's all we need right now. So minus 2 times 0 is 0. Minus 2 times 0 is 0. Minus 2 times minus 1/2 is positive 1. Minus 2 times a negative 3 is positive 6. Minus 2 times 1 is minus 2. And minus 2 times 3 halves is negative 3. Get out of there. This just drives me nuts. That is supposed to be a negative. Okay, it's really ugly. Both of those are negatives. They just aren't in very good places. This then gives us our inverse matrix. Let me, before I go any further, make sure I did it right. Okay, I was looking at the wrong one. Minus 1, 1, 0. Minus 1, 0, 1, 6 minus 2 minus 3. Perfect. Okay, so what do we do now? We do take this matrix here, that inverse matrix here, negative 1, 1, 0, negative 1, 0, 1, and 6, negative 2, negative 3, and multiply that by, first we'll multiply it by negative 1, 1, negative 2, negative 1, 1, negative 2. Now, 3 by 3 by 3 by 1 is going to produce a 3 by 1. 3 rows, 1 column. So let's go to it. negative 1, the first entry here, 1, 1 entry, first row by first column, negative 1 times, get out of there, negative 1 times negative 1 is plus 1, plus 1 times 1 is 1, so that's 2, and then it'll be a 0 times 2, so that's a 2. Alright. The 2, 1 entry here, second row times first column, that would be a 1 plus 0 plus 1, that's a 2. And the third column would be a minus 6, minus 2 would be minus 8, plus 6 would be a minus 2. Okay, so that first set of equations, your x, y, z, a unique solution is equal to 2, 2, negative 2. I know those 2's look like almost like 3's. I can't help it. The pen just sort of drags. Sorry. Eyes are so dry. Let me see if just water will help. I want to splash them in my face. Okay. Now, the second set of equations do the same thing. Okay. Now, why it does that, I don't know. Okay. Alright. So we take that same equation here, minus 1, 1, 0, minus 1, 0, 1, and 6, minus 2, minus 3. And we'll multiply that by 485. And that also is a 3 by 3 by 3 by 1 will give you a 3 by 1, which is what we'd expect. Now, that is a 1 there. Let me just make it clearer. Okay. Negative 1 times 4 is negative 4 plus 8 is positive 4 because the last was a 0. Negative 4 plus 8 is 4 again. And 24 minus 10 would be 14. Minus 15 would be a minus 1. So that would give you an x, y, z of okay. I'm doing something wrong. I must have copied something wrong here. Let me see. The first one is that, and that gave us a, let me do the second one here. Minus 2 plus 1, minus 1 minus 1 times minus 1 is plus 1 plus 0. That's a minus 1. Okay, sorry about that. I don't know where my brain is today. Okay, this one's a minus 1. Well, let me try it again. Okay, minus 1 times minus 1 is plus 1, and 1 times minus 2 is minus 2, so that'll be a minus 1. Okay. Yeah, that gave the right answer. This one I must have done something else stupid here. Okay. Alright, let me erase again. Okay, let's try it one more time. Okay, make sure I copied the thing right. I think I did. And okay. Yeah. Okay, let's do it. Minus 4 plus 8 is plus 4. Got it. Minus 4 plus 5 is plus 1. I was doing the wrong column. 24 minus 16 is 8. Minus 15 is minus 7. I don't know where my brain was. And that's right. 4, 1, negative 7. Now, we didn't do the last one, the 0, 0, 0. I don't have room to do it, but well, yes, I do. I'll do it right over here. And it's hardly worth writing it down. So minus 1, 1, 0. Minus 1, 0, 1. 6 minus 2, 3. Minus 3. And I'm going to multiply that by 0, 0, 0. And I hope you can see what's going to happen. That's going to be 0 plus 0 plus 0, 0. 0 plus 0 plus 0, 0. 0 plus 0 plus 0, 0. Okay. Remember we said if this was an invertible matrix, it is. So therefore it has a unique solution. It does. And the only solution for an homogeneous system, certainly one solution is always 0, 0, 0, the trivial solution. But since this has to be a unique solution, that is the only solution. So 0, 0, 0 is the last one. All right, finally. That finishes 2.3. Homework exercises here would be any of the odds 1 through 5. They're all at calcchat.com. Any of the odds 7 through 29. They're all at calcchat. They say you might need a utility function, a computer, a graphing calculator, something like that for 27, 29. I think you can do it without it, but it may be tedious. If it gets too tedious, just do the others. Any of the odds 31 to 35, 37 or 39, they're all at CalcChat. 41 or 43, both at CalcChat. 45 or 47, they're both at CalcChat. 49 or 51, they're both at CalcChat. 53 is at CalcChat, 55 is at CalcChat, 57 is at CalcChat, 59 is at CalcChat, 61 is at CalcChat, and then any of the odds 63 to 69, they should all be at CalcChat. 71 should be at CalcChat, and any of the odds 73 through 83. They should all be at CalcChat. All right. Any questions on 2.3? All right. Ready to start 2.4. At least I say we are. My throat doesn't feel like I'm ready to start it. So let me see if I can do something to make it feel better. All right. No questions on this? So the only time, basically, that doing this technique, finding the inverse of your coefficient matrix, and then multiplying by your constant vector to give your solutions, the time that makes sense is when you've got the same set of coefficient matrix for, I would say 3 or more non-trivial constants. That 0, 0, 0 is, you could have looked at that and said the answer is, if that has an inverse, which it does, that's going to be 0, 0, 0. Especially since they told us that they have a unique solution. It had to be 0, 0, 0. All right. So let's move on to 2.4. All right. The Objectives here, factor a matrix into a product of elementary matrices, and then we'll find and use an LU factorization. We'll tell you what LU stands for in a little bit, of a matrix to solve a system of linear equations. Okay. Review. Section 1.2 introduced 3 elementary row operations for matrices. We just did them. Interchange 2 rows, perfectly legal. Multiply a row by a non-zero constant. We did that in the last one a couple of times, perfectly legal. And add a multiple of one row to another row. Okay? Now, in this section, you'll see how to use matrix multiplication to perform those same operations. Okay, so first a little bit of a definition. Definition of an elementary matrix. It'll probably be easier for you to read, not necessarily easier for me to type, but easier for you to read if I do this way. Now there's one subscript here that I know I won't be able to do, but here's what it is. So first, an n by n timeout. What does that mean? Square matrix. Square matrix. Okay? Warning. Has to be a square matrix. Now, by using that symbol to be a square, that doesn't really look like a square, but let's just imagine it is. Where I get that is when I was growing up, I had a younger brother, still have, and an older brother and a younger sister. Okay? My older brother and I were pretty close. We were about only 2 years apart, but I was big for my age. He was small for his age, sort of. So we basically grew up together and basically were almost like best friends. We just did everything together. My younger brother came along about 3.5 years after me, so there's quite a age gap. My older brother did pretty well in school. He never worked at it too hard, but he did pretty well. And then I did fairly well. My younger brother just wanted to be different. Okay, so he wanted to do well because he wanted to please my parents, but he also wanted to be different. So he became sort of the wild child. Okay, there were several factors that went into that. I don't know what they all are, but you know, he definitely did. So going on, as we all three grew up some, my older brother got a little more on the wild side too, and I stayed Mr. Dull. Okay, so my younger brother thought I was being an older brother, and my older brother, you know, and he could do some things together, and they enjoyed that. I never participated that much, so I became a square. Okay, and he said, "You're an L7. This is an L, that's a 7. I became a square." So after a while, he started calling me L7. Later, that shortened just to L. Hey, L. Okay, and sometimes a day, he'll still catch himself calling me, "Hey, L," because I was the square of the family. But anyway, that's the square, L7. Okay, definitely not very linear algebra-ish, but there it is. An m by m matrix, a square matrix, is an elementary matrix when it can be obtained from the identity matrix Now it has to be the right size. This is where it should be a subscript. I can't do a subscript. I sub n. That's what that stands for. By a single elementary row operation. Okay. That's the definition of an elementary matrix. Okay. Let's string it out here so maybe it'll be not quite as junky on the page. A square matrix is an elementary matrix when it can be obtained from the, I knew that didn't look right, identity matrix. Okay, from the identity matrix I sub n, that's the sub there, by a single elementary row operation. That means take an I, square matrix I, identity matrix, swap two rows, any two rows. That would produce an elementary matrix. Or multiply or divide by a non-zero, a single row by a non-zero constant. That would be an elementary matrix. Okay? Or add a multiple of one row to another row. That would be an elementary matrix. The phone downstairs is just ringing its ears off, and I don't know why, but anyway, I'll take care of that. Maybe I don't have time at lunch. Sometime this afternoon I'll check on that. All right, so let's do example 1. Okay, now, I know some of you don't have books, so I'll write these out for you. And what your task is to tell me whether these are elementary matrices or not. Okay, let me get my drawing tool going. Here's the first of those matrices. 1, 0, 0, 0, 3, 0, and 0, 0, 1. Is that an elementary matrix? You tell me. Anybody? Help me, folks. Is that an elementary matrix? Earth to class, come in, please. Anyone there? Can you hear me? Have I lost sound? Okay, good. Is that an elementary matrix? What you think? Make a guess, yes or no? I think I heard a very hesitant yes. And yes, it is. It is an elementary matrix. Why? You got it by multiplying the identity matrix, the second row in the identity matrix, by 3. Remember, that's one of your elementary row operations. Multiply a row by a non-zero constant. Multiplying the middle row of the identity matrix by 3 produces this matrix. So yes, that is. How about this one? 1, 0, 0, 0, 1, 0. Is that an elementary matrix? Anybody? Yes or no? No. Why not? It's not square. Okay? It's got to be square to be an elementary matrix. This is not square. So if I can find my pen, not square. Okay, couldn't be an L7. Okay. How about this one? 1, 0, 0, 0, 1, 0, 0, 0, 0. Is that an elementary matrix? Okay, almost is, but not quite, and here's why. You multiplied the third row of your identity matrix by 0. And remember, your acceptable operation is to multiply a row by a non-zero constant. So no, this is not an elementary matrix. Okay? Number D, or letter D. 1, 0, 0, 0, 0, 1, and 1, 0, 1, 0. Is that an elementary matrix? Anybody? Last entry in there is a 0. It doesn't much look like one, but it is a 0. Yay or nay? All right, I heard somebody answer, but I couldn't tell what they said. It is a yay. What you did was exchange the second and third rows. That's a legitimate elementary row operation, exchanging two rows. Okay, so yes, this is an elementary matrix. If I could find my, there it is. That one is. E. 1, 0, 2, 1. Is that an elementary matrix? Anybody? Anyone? Okay, yes. Your helper there is telling you, yes, it is. Okay. Now, why is that? Because you can multiply. Think of starting with the identity matrix 1, 0, 0, 1. Multiply the top row by 2 and add to the second row. Yep, that's exactly right. That is an elementary matrix. And number F, or letter F. 1, 0, 0, 0, 2, 0, and 0, 0, minus 1. Is that an elementary matrix? Anybody? Okay. Any help? Your helper isn't answering now, is she? Or he? Okay. Now, this one is not. Okay. And here's why it's not. You could have gotten this by multiplying the second row by 2. You could have gotten this by multiplying the third row by minus 1, or dividing by minus 1. Either one would be fine. But the thing is, it's this little word here, a single elementary row operation. This required 2 elementary row operations, therefore it's not an elementary matrix. Close to 1, but not right. If that had been a plus 1, for sure. If that would have been a positive 1 here, for sure. But you can't have 2 elementary row operations on the same matrix. That will not be an elementary matrix. So either one of those would have made it, but both of them, no. Okay? So if you look in your book, the top one is, A is, B is not, C is not, D is, E is, and F is not. Okay. Now, how are we doing? Okay, we got time. Elementary matrices are useful because they enable you to use matrix multiplication to perform elementary row operations. Well, guess what? It's easier to just do the operation, but we'll see that's true. And we'll see there's a reason for all this. It actually starts out being really like, what's the point for doing all this? Well, there is a point, and we'll get to it. Okay? And this is going to illustrate what it's talking about. So, I'm going to start with an elementary matrix. And we're going to call these E. Okay? This elementary matrix will be this one. 0, 1, 0, 1, 0, 0, and 0, 0, 1. But before we go any further, I want you to confirm for me whether you think that really is an elementary matrix or not. What do you think? Anybody? No, that one's a yay, because all you did was exchange row 1 and row 2. That's all you did. That is an elementary matrix. Okay? Now here's your matrix A. This doesn't have to be elementary. It's just any old matrix A. 0, 2, 1, 1, minus 3, 6, 3, 2, negative 1. Yuck, that drives me nuts. Okay? Now we're going to multiply these two matrices together. Okay? Now, number one, can you multiply those two together? Is that a legitimate operation? Yeah, that's a 3 by 3. This is a 3 by 3. The number of columns of this is equal to the number of rows of that, so you can do it, and that'll leave you with a 3 by 3. Okay, so yes, you can multiply them, and your result will be a 3 by 3. Okay, so for the first row, first column, we'll take the first row of E, and by the way, we're calling this one A, okay, by the first column of A. 0 times 0 is 0, 1 times 1 is 1, 0 times 3 is 3. So that leaves us a 1. The 1, 2 entry here would be first row here, second column here. 0 times 2 is 0, 1 times minus 3 is minus 3, 0 times 2 is 0, so that's a minus 3. Next, the 1, 3 entry here, first row, third column would be first row here, third column here. 0 times 1 is 0, 1 times 6 is 6, and 0 times minus 1 is 0, so that's just going to be a 6. Okay? 2, 1 entry, this entry right here, second row, first column, that would be second row here, first column there. 1 times 0 is 0, 0 times 0 is 0, 0 times 1 is 0, and 0 times 3 is 0. That adds to nothing, 0. Okay, the 2, 2 entry here, second row, second column, will be second row here, second column here. 1 times 2 is 2, plus 0, that's just going to be a 2. The 2, 3 entry here will be second row here, third column here. This will be 1 times 1 is 1, plus 0, so that's going to be a 1. Alright, excuse me, I think I'm going to have one more swig of water. Goodness gracious, I thought, or Coke or something. Alright, the 3, 1 entry here, third row, first column, is going to be third row here times first column here. That would be a 0 plus a 0 plus a 3. The 3, 2 entry here would be third row here, second column here, 0 plus 0 plus 2. And the third entry here, the 3, 3 entry, is third row, third column, 0, 0, minus 1. Step back for a moment and see what happened to matrix A when you multiply by that elementary matrix. What happened? The third row stayed the same. The first and second row swapped. Look at that. Do you see that? Well, guess what happened? When you multiply by elementary matrix, which the first and second row swapped by A, you swap the first and second row of A. That's what happened. That's what an elementary row matrix does for you. It does the very elementary row operation to A that you did to the identity matrix to make that E, that elementary matrix. Okay. Let's do the B one. Here the elementary, or at least a matrix. You tell me whether it's elementary or not. A 1, 0, 0. A 0, 1 half, 0. That's supposed to be, I don't know why this pen does that. I have to go incredibly slowly to keep it from doing something dumb like that. 1 divided by 2. No, and if I go too slowly, it won't write. That's what drives me nuts. Okay, 1 half, 0, 0, 0, 1. Question, is that an elementary matrix? Anybody? That one is. All you did was multiply your identity matrix. See the top rows of the identity matrix row, bottom rows of the identity matrix row. You multiplied the middle row 0, 1, 0 by 1 half. And that's an elementary row operation. That makes that an elementary matrix. Okay? Now, I'm going to multiply that by, look at this matrix. Now here's the deal. Elementary matrix has to be square, but what we're multiplying by doesn't have to be square. This is a 1, 0, 4, no, minus 4, 1, 0, 2, 6, negative 4, 0, 2, 6, negative 4, 0, 1, 3, 1. Okay? But you got to ask yourself, can you even do this? Well, let's see if you can. It's so hard to write with this thing. This is a 3 by 3. This is a 3 by 4. Yes, the 3's go out, and that leaves you a 3 by 4. So yeah, this will produce a 3 by 4 matrix. 3 rows, but 4 columns. Okay. Yeah, got 2 minutes. Let's see if we can do this. 1, 1 entry, first row, first column, is first row times the first column. That gives you a 1 and only a 1. Okay? The first row times the second column. That gives you a 0 and only a 0. First row, third column. First row times the third column gives you a minus 4 plus 0 plus 0. That's a minus 4. First row, fourth column. First row by fourth column here. That gives you a 1 plus 0 plus 0. That would be a 1. Okay? 2, 1 entry. Second row here, first column. Second row here, first column there. 0 plus 0 plus 0. That's a 0. Second row, second column. Second row here, second column here. 0, 1, 0. Okay? Whew, goodness gracious. 0, the second row, third column, second row here, third column there, 0, 3, 0. That would just be a 3, and then the last one would be a 0. Second row, fourth column, 0, minus 2, 0, that's a minus 2. Whew. Goodness, I'm about out of gas. Okay, third row, first column, 0, 0, 0. Third row, second column, 0, 0, 1. Third row, third column, 0, 0, 3. And third row, fourth column, 0, 0, 1. Timeout. How does this matrix A over here compare to that one? Top row's the same, bottom row's the same. The middle row is exactly 1/2 this one. Well, that's exactly what you did there. You did an elementary row operation by doing a multiplication with an elementary matrix that did that row you got from that row operation. Okay, we have run out of time. Sorry about that. I'd hoped to get the third one done. I'm almost glad we didn't. I'm just about out of gas here. All right, we will pick up next time with on 2.4, page 75, the C part there. Let's see if we did enough to have any homework exercises here. I hope we did. This is a long section. Okay, I think you can do any of the odds 1 through 7. That's just determining whether they're elementary matrices or not. It sounded like y'all need to practice on those a little bit. And then you can try doing, and by the way, all those are at Calc Chat. You can look at doing maybe 9 or 11. If you can't do it, hang on, and I think you can. But if you're having trouble, hang on, and maybe after we do the next couple of examples, you'll see how to do it. All right, any questions? All right, if not, then I'm going to stop the sharing. Sick and tired of sharing. And unless you have any last thoughts or parting shots, I'm going to end the session for all of us. This is the last time I'll see the 3 of you this week, so have a good weekend, and we'll see all 3 of you Monday. I think it's going to be a rainy weekend, so try to get some linear algebra, Cal 3, or differential equations done, and we'll see you. I'll try to get grading done. We'll see you on Monday. All right, take care. Be safe. Bye-bye.